We had a horrific incident where the Kapton tape on the battery pack had ripped. We were supposed to take it out to SpaceX to test. A few hours later, like the whole vehicle we built was just burned to crisp. We have roughly 20 days before we have to go to SpaceX. We have to rebuild the whole thing from scratch. We thought, are we going to give up or are we going to actually build this thing?
Imagine this: in someday we'll have some manufacturing capability on the moon. I think that's the ultimate vision.
I'm very excited to see all the cool things that are going to come from AI.
So it's almost like an engineering world model. Right now, you're building world models for robotics and AI, but we're trying to build a manufacturing world model.
We basically are unlocking the human innovation speed. I don't think people can say right now we can do one-man company for every industry. That's impossible. But with the help of us, I think there's a chance.
Before we started at Aether, both of us were many years ago graduate students at MIT, and we were working on the SpaceX Hyperloop project. And I'm not sure if folks know more about the Hyperloop, but back then Elon Musk announced sort of a high-speed train concept, and I was inspired by it. Maybe one day we can have a Hyperloop, taking us from like Houston to Dallas or like LA to San Francisco pretty quickly. And when I came to MIT, I had met Bowen because we both were in different departments. I was in the media lab. He was in the mechanical engineering department. And I remember before the pandemic, we're trying to figure out, can we build this new Hyperloop pod for Elon's like competition? And we had this initial design of a levitating vehicle that had used some air bearings and had electric propulsion in there. And we had a team of about 30 people on this. And it was crazy. Within like 3 to 6 months, we had designed and built an entire autonomous car as part of the SpaceX challenge. Bowen was the lead for our mechanical engineering team, and we had a group of amazing folks from all departments like electrical engineering, physics, And then, during this time, I had built this battery pack and we had developed this prototype. And about a few months before the competition, 1 month actually, we were supposed to take it out to SpaceX to test. We had a horrific incident where the Kapton tape, I think, on the battery pack had ripped, and the whole 440-volt battery just shorted across the rails. And at that time, there was just flames running in this vehicle. And it was one of those incidents where, oh my God, like we had a real battery fire happening, and the fire truck came by, put the fire out. And, a few hours later, like the whole vehicle we built was just burned to crisp. I still have memories about this where the whole team, we got together, Bowen, me, we had about the rest of 15 plus people came together that same evening. And we looked at the map, we looked at the calendar, like we have roughly 20 days before we have to go to SpaceX. We have to rebuild the whole thing from scratch. And we thought, are we going to give up or are we going to actually build this thing? And we ended up redesigning the whole vehicle. And I remember Bowen was on the computer with SolidWorks, just designing the whole chassis system with the team. And we had a new design of a chassis built within, I think, 3 or 4 days. We had the pneumatics rebuilt from scratch in about a week. And we had the battery pack rebuilt within like 3 or 4 days. The whole electronics redesigned in about a week. And it was literally, I think, 2 or 3 days before the competition, we had all the pieces put together. And then we shipped this in a crate out of Boston and Cambridge straight to LA. And then we went to SpaceX the next week, with a brand new pod, right? And what's crazier was that they had no idea we had to rebuild a pod. And we went through the whole design iteration cycle of the hundreds of tests that SpaceX put us through. And then we won the competition in the US. We were number one in the US. And it's like insane that the level of engineering that went into that and the level of passion is what kind of inspired us to even start this entire company. And I think now, fast forward like 10 years later, we're now reinventing like factories. We went from autonomous cars to now building autonomous factories.
Question about that. When that fire occurred, my impression is that served as a bit of a forcing function that caused you to revisit the principles of design in the first place. It sounds like you didn't just recreate what you had already made. It required you to be more efficient in the rebuild and redesign. Can you talk about that a little bit?
I think it's just a forced opportunity for us. So first thing first is that we evaluate the timeline. There's a possibility because nonetheless, while we're waiting for those raw materials or pneumatic system to be rebuilt, we will have a lead time to do the design review anyway. At the first iteration, we always are unsatisfied with a lot of design decisions for the first place. And why not take this time to revisit most of the design? And then if it's still possible to change that, we change that. For one huge improvement that we had at that time is for the installation of the entire battery package, right? So at the first iteration, the battery space is quite small, so that while you install or uninstall the battery package, you will always have a chance to rip up something. It's either a Taptone tape or a cable, right? You will always have a safety concerns. But the for the second time we do, it's just taking all those experience. I would like to say it's almost perfect this time, right? So just one example. The takeaway from this sort of experience is actually quite important. Is that if we want to work with a team, or we want to build a team, we want to build a team that all people here had the same mindset. But most importantly is that we align on certain objects, but we are never satisfied. So those are the people or the teams that we are trying to build at Acer this time as well. Is that because we see the status quo of manufacturing, and we know it's not its ultimate form, and we want to make it ultimate form, and we want to you know get our hands very dirty, very oily on the shop floor,
Yeah.
right? Because we are unsatisfied with this triple knowledge thing. We're unsatisfied with that. Why this so hard to build things here, right? So that's I think that's the spirit. We're in a very good shape to passing on, and while the team gets larger and larger, we hopefully we still have to maintain this.
Yeah.
Yeah.
I mean, the culture of that sort
Yeah.
of mind in hand is that thing
Yeah.
that we kind of live by. And I think even though we met at MIT, it's crazy that like even since then we have the same kind of like desire to really kind of change how things work. I mean, with Hyperloop, right? We really think that one day we'll have a system like that, right? I mean, we're right here in Austin, and there's a whole Hyperloop Plaza now, right behind Tesla's Gigafactory, and we were just hanging out at the local areas here and just talking about, wow, 10 years ago we were working on this. Now there's an actual system maybe being built with the Boring Company. And I think, for Bone and I, we really think that manufacturing is going to go to that same level of rebuild, right? So like just like we've rebuilt this pod, I think manufacturing needs to be rebuilt ground up, first principles, and how do you redesign the factory? And I think we cannot fall into the trap of just leaning into what we used to do to change manufacturing. And I think that is the key, is that it's a mindset change, it's a shift in sort of how we build and shift in how we apply software to hardware, and also how we leverage AI to now make that whole process even more efficient. It seems to me that, especially in the US, we have a lack of many suppliers who are able to do complicated components. And we have essentially have been exploring ways to bring that back to the US. And what do you think would be like the most important things to start with first? Would it be, building a better supply chain for tooling and die, or is it improving our supply chain for post-processing? What are some of the key bottlenecks you think we're facing right now we need to solve first?
From my perspective, as a business development professional, I'm thinking about the market opportunity, thinking about the state of the U.S., our manufacturing and industrial capacity, and the backdrop of the AI infrastructure build out. I've been kind of pounding the table about really wanting to step into the utilities and power generation supply chain. It's pretty well known that there's a multi-month, if not multi-year backlog for pretty basic but critical components. So switchgear, transformers, bushings, studs, things like that can be manufactured by a group like Aether to step in and pick up some of that slack. Because when we go to the next step of actually outfitting these data centers that everybody's very excited about, if there's no power to run them, who cares? So equipping the utilities and power generation companies and the distribution companies with the ability to actually step in and provide power to those data centers, I think is really, really important. I'm very excited to see all the cool things that are going to come from AI, but we need to power it.
After visiting the NVIDIA conference, last week in SF, I was just kind of blown away with the amount of people looking at the capacity constraints that are going to need to be resolved for data centers. And you can see that every single supplier is struggling with sort of getting enough capacity to support the data center build out. On top of that, the cooling infrastructure is completely changed, where for data centers, most of these components require gigawatts of power. And I think at that point, you have to cool them properly, and the thermal constraints are also high. So, looking at things like how do you machine these sort of manifolds that go into the data center server clusters, properly machine them to spec, to high tolerance, to high flatness. New methods like flow drilling are a huge area of importance. I'm just curious, like, what are some of the areas that, as this infrastructure build out evolves, that we need to kind of like, learn more about to ensure that ensure we can support the capacity?
Yeah. So I think Jake just covered
Yeah.
what's the demand side. I'm more thinking of the supply side, right? I think the fundamental principle is that anything works in China or Indian manufacturing powerhouse will not work in the US. So it needs a total new model to make it here. Basically, you just need to make things autonomous and less rely on those triple knowledge.
Mm.
You have to making sure AI is running the entire show of it. The physical AI is running the entire show of it. But this will also give the entire new opportunity, which is like once this new model is set, right? It will be it will be intrinsically scalable. Your transfer of experience, the speed of propagation, is actually will be faster here. So that's one, but there will be a big technology or supply capability hurdles. And two is basically there's a new chance of doing it in a new way that can be the ultimate form for the manufacturing. Imagine this, right? Just thinking extreme, but first principle is that in someday we'll have some manufacturing capability on the moon, right? But that has to be autonomous. So basically, what I'm thinking is here at the U.S. soil is basically a testing ground for what's going to happen in the moon and Mars,
Mhm.
right? So you have to make it at least this autonomous in order to get to the moon, and you have to make it more autonomous when you get into Mars.
Mhm.
So that's the test ground here, right?
You mentioned
Yeah.
the tribal knowledge
Yes, tribal
that
knowledge.
is
Yeah.
that exists in Asia
Yes.
in manufacturing
Mhm.
facilities in China. What is the best way that you guys think to actually bring that tribal knowledge back and kind of reestablish it, reconstitute it in the U.S.?
Everything on the shop floor is a recipe. So there's nothing like just put a little bit more power on this. There's nothing like that. Everything has to be describable. That's the first principle. So the triple knowledge is just I think it's just a term. But to be honest, the triple knowledge can actually be first being breakdown into quantifiable pieces or tasks. That's where the standardization will happening. And while we doing the standardization of those triple knowledge, we also think ahead. Some of them can be autonomous, some of them can be co-pilot, right? So we think this as a constraint problem, but it's a quantifiable constraint problem. That's the first step of the mindset readiness, right? Then if we have that, then basically we can build the entire physical AI or agentic workflow system, and also in combination with like the help of AI to generate those processes, right? Then you will have a entire digital recipe that's fully describable, that's fully can be stored on the data center, and also it can be feedback loop self improved upon the real time data on the real time machines or robotics, or the feedback of the skilled labor on the shop floor. Yeah.
So it's almost like
Yeah.
an engineering world model, right? So
Yes.
like, right now you're building world models for robotics and AI, but we're trying to build a manufacturing world model, right? So you imagine a shop floor with like 100 CNC machines, CNC machines are great at subtractive manufacturing. With Aether, we're trying to automate that CNC category. But what I've noticed is that, in order to truly bring that tribal knowledge back to the US, you need to bake this sort of process knowledge inside of the sort of the system architecture of our world model. And so you're bringing all the machine tools, the parameters, the cutting tool parameters, and baking it inside of our software. And then essentially all the process knowledge you get from like the CAM programmers are now baked into this closed loop execution system.
Yeah.
And I think if we do that, then you can truly not only just reshore, but also bring the unit economics to a point where you can actually be self-sustaining in high labor cost kind
Right.
of countries. And I think that is the biggest thing I'm noticing here is there's been a lot of excitement about manufacturing. And I think if we don't solve the sort of the problem from a first principles perspective, we're still going to continue to offshore our entire supply chain.
Yeah. And when we amongst ourselves refer to tribal knowledge, we have a set of instincts about what that means. But for those who are less familiar with manufacturing or what we are doing at Aether, maybe Vic, you could unpack what we mean by tribal knowledge. What are the elements of tribal knowledge that we are trying to bake into the platform?
Yeah, so, when I visited a bunch of factories, both in the US and in Asia, a lot of times you visit like a CNC factory, which may have like 500 machines with 1,000 people in Asia running 2 shifts, right? And most of the machinists and process engineers know how to machine a part really inherently because they've been in the factory for a long time. Especially in Asia, you have generations upon generations have grown up building components in a factory. It's basically a sense of pride to be able to machine stuff. And I think that level of expertise baked into the sort of the brains of the process engineers is sort of the core element that we're trying to understand better because, in the US, we just don't have that skilled labor to, create that level of efficiency on our soil. And I think from my perspective, the first thing is to really understand what are those process techniques that we could really start to quantify. As Bowen mentioned, like everything is a recipe on the shop floor. Not just the CAM programming and possibility, but also the how do you change your fixtures? How do you design new chucks to support your CNC machines? Also looking at ways to, if you have a multi-faceted facility, we have a CNC machine, EDM machine, a 3D printer. How do you use all these machines together to optimize your design? And sometimes you may have to use a 3-axis machine or 5-axis machine to machine your part. If I take a 3D geometry of some aluminum or some titanium component, you want to figure out how do you efficiently carve that material out of that block to make your component. And I think if we can do that in a very quantifiable way and bake in the process knowledge all the way from the 3D step file down to the G code, I think that's going to be the unlock for this entire industry to redefine the manufacturing ecosystem and build that world model we're hoping to do.
So basically taking the tried and true practice, trial and error experience of a machinist and bake that into our autonomous process generator software so that all of that kind of hands-on experience is now programmatic.
Exactly.
Yeah. And to add on that, so I think what we call so-called triple knowledge will have two categories, right? One is the process triple knowledge, and the other is operation, right? So process means what's the definition of making these parts right. The operation is other. So what's the best execution to make these parts along with the other 1,000 parts on the shop floor, right? So that's a system problem as well. But then to go back one little step is that so for triple knowledge, the most scarce things in the past is a lot of things are done, but they are never recorded. They are never thought of in the first principle manner. So that's why they call it triple knowledge, right? But then what we have to do, I think, is to truly understand what does each step means at the process stage and at the execution stage. And then we reverse engineer this with AI and code in order to make this, work in the future, and it can be scalable, can be self-improved.
One thing I'm noticing is that in the sector of like advanced manufacturing, right? I mean, we're looking at industries like robotics, data centers, medical, oil and gas, anything that requires high tolerance kind of components. That's kind of our specialty. Is that I think the problem that I'm noticing right now is like, you can build a marketplace to kind of sell components and at a faster, cheaper way. But if you don't understand the true geometry of these parts, you're only going to go so far. And on top of that, a lot of our clients are in the high precision industry, building components for a robot or data centers that require high precision. So how do we bake in like high precision tolerances, and how do we understand that in our software? Like how does our software handle that compared to other vendors out there?
From the end customer perspective, they want the results to be so complex parts to be produced. It's on time. they want it to be on spec on every critical to quality callouts on the drawing. They also sometimes they want it cost effective while they going into the MP mass production stages, right? So that's what they want. But oftentimes it's like at the end of the day, they can produce these parts with some shop floor, but the lead time is gone for several weeks, up to like 8 weeks or even month, right? And then that's a losing opportunity at this era, right? So everything has to move very fast in order to catch up. Every lead time is related back to the process itself, because process to make a part is a recipe of this part. It dictates on the timing, what's the total cycle time of this part, what's the total lead time on getting the special tools, on getting the special inspection equipments, and then this part can be produced and can be vetted in-house and shipped to our customer, right? So this is the deterministic process. At least for a single part, it's a deterministic process. First thing first is that we need to have the full control of from the beginning to the end, right? So this is definitely needed. So that's why a lot of marketplace doesn't work, is because marketplace is just a broker service that you often see is the more complex parts or more demanding projects they experience or they encountered, the worst results is coming out. So it's because the marketplace, their back end, their supply chain is always tiered.
They
right?
don't vertically integrate.
They don't. So why is they don't vertical? They don't integrate anything.
Yeah.
They just send those like leads information to the collaborative shops networks, and then the who has the lowest price and who bid for the the shortest lead time will win that project. However, in order to win, a lot of shop is actually encounter those game theory, right? So they just become the prison dilemma, is that they have to lie in order to win. So that's a problem.
So on that topic,
Yeah.
we recently visited one of our clients who told us a story of how shops, many shops just end up lying to them to win the deal.
Yeah.
And then they lose that opportunity because the lead times kept getting pushed out further and further because there's no transparency in their supply chain, which is really unfortunate because, I think if we were to have more transparency in the process of how we make the part and show them when it's being produced, how it's being produced, it'll give confidence to the client. And I think, at the end of the game, it's building trust, right?
Yeah.
I think in this industry right now, I think the supply chain has a lot of components that are kind of unknown to the end user. And so they don't know what's going on. Therefore, there's a lot of essentially, variables that are at play. And I think if we can sort of create a transparent sort of a system that can allow them to see the status of the parts being processed, the G code be generated, all the way down to supply chain planning, I think that would give a lot of confidence and build that trust with the client. Yeah. And ultimately, back to your point, I think it's about lead time. I think if we can figure out a way to continue to win on lead time as we do right now with our clients, I think the matter is, how do you continue to scale that to more and more factories? Because ultimately, you're going to need a lot of factories to support super fast lead times. And I think this is where I think decentralized manufacturing plays a big role. Like, can you localize manufacturing shops where, right now there's thousands of shops opening up in the US, but I think they lack a lot of the sort of the vertical integration in the software stack to really make them truly autonomous. And I think this is where we can come in and say, look, here's a shop that's opening up with several, tens of CNC machines. Let's just automate them, or let's just deploy our software stack on them and essentially make them twice as efficient on OEE. People obviously want to have factories, but they don't really think about the post-processing needs of the factory. Some people still are shipping parts out of Texas to California or other parts of the US to get something anodized and come back. And that adds to the lead time. Now, if we can figure out a way to, like you said, like combine all this together within a single region, either Texas, Mexico, or within our sort of vicinity, we can leverage our interstate highways to basically create a logistics system that can quickly deliver parts at speed. And I think, I keep going back to Amazon as a reference. Like, Amazon has launched their 2-day shipping, Amazon Prime, and it's always been a popular thing. And I think, we don't have that for precision components. Like, imagine if we could change how precision components get made and shipped you have guaranteed delivery within 2 days. We joked with one of our clients that they wanted a lead time pass, right? Like,
Yeah.
imagine if we can provide a lead time pass where they can always rely on this consistent lead time over and over again because we know we can deliver. And I think if we can create a network of these facilities that can handle machining, post-processing, quality, all within the same roof or within vicinity, we can really change how the entire unit economics work for the lead
Yeah.
time of these
It's
components.
just like the relationship between Shenzhen and Dongguan is
Yeah.
they're adjacent, like
Yeah.
Texas and Monterey.
Yeah.
It's the it's another Dongguan Shenzhen relationship,
Yeah.
and that's a true Tex-Mex recipe we are providing.
Tex-Mex.
Yeah.
The one term that keeps coming up a lot when I talk to like a lot of our clients is that they deal with a lot of high mix parts. And how do we describe high mix? Is that something? The way I'm thinking about it is that when we deal with traditional factory, especially high volume in like Asia, right? You have, let's say, iPhone production happening in the billions of units that are being planned, and I think that's considered like high volume, but there's not a high variety of SKUs. And I think when you look at our industry that we're in, especially with CNC machining and subtractive manufacturing, most of our clients have a, like, I would say, medium to low volume, but then the mix is super high.
Yeah.
I think that is really hard to automate. And I think what's key about this tool that we've been making is that you can now throw hundreds of parts at our APG software in like within like a minute, and it'll analyze all geometries in a few minutes and just give you a process planning for all of them. I think that enables the sort of high mix industry to really scale, because a big problem in the shop is the quoting process of how do you take in thousands of geometries and quote them accurately and ensure there's enough capacity at the factory to make those volumes. So I think what we're doing here is really different because the high mix sector needs a solution like this to be able to scale their factory to be at volume.
Yeah. I mean, we're sort of in the foothills of building the thing that Elon has been talking about for quite a while, which is the factory as the product, and a factory that can sort of self reconfigure based on the requirements that are being fed in by users, essentially. And so you can very quickly pivot from robotic SKUs to HVAC SKUs to utilities SKUs on the fly as needed, on demand, and still maintain excellent costs, excellent lead times, excellent precision, all the fault tolerances that are required for those parts, and the factory kind of reorganizes itself around those demands. And it sounds like science fiction, and it has been until now. And we're in the process of actually bringing that technology to market, which is very exciting. But I'm also curious what you guys think about what are some of the cool things that, aside from the technology within APG and FacOS, which we can explore a bit more, but what are some of the things that you envision this technology enabling? Not just the deep tech in the weeds kind of nerdery that we get excited about amongst ourselves, but like, why should anybody else out in the world care about this?
This is a great question. I think the way I think about it is that if we truly believe that the future is going to be fully autonomous, robots, autonomous vehicles, maybe you have network of data centers out there. The thing is that we are still struggling with the supply chain, as we can notice even with the pandemic and with the current crisis in the Middle East. There's just so much happening that's relevant to our supply chain, and if we don't resolve these sort of bottlenecks that we face, and the fundamental is like everything that we make right now comes from some supplier that has some network all around the globe. And I think if we need to figure out how to sort of resolve the sort of the capacity issues and constraints issues we face in the supply chain. But on top of that, I think to kind of execute even back to what Elon has talked about with building factories in space and maybe putting data centers in space, all these components require machine parts. And if you think about it, the machine parts sector is a multi-trillion-dollar industry globally, and everyone needs metal components, whether it's they're making the next future robot or making the next future component that goes into even a dishwasher or refrigerator. The volume of sort of impact we could have by changing how we process these mechanical components can change the future of how quickly we can iterate at speed. And a lot of times companies are facing multi-months of cycle times to basically iterate on their part design, right? We're reducing that cycle to be within 2 to 3 weeks, if not less, with our software stack, which means that you have more time to iterate on your design and also more time to kind of it put robots or new versions of your tool out there. So I think, back to your point, Jake, I think that the main thing that I see is sort of the speed of iteration is going to change dramatically, and that's going to unlock a whole new set of designs, prototypes, systems that could be deployed and tested at scale because the number of components that we're going to be making is going to just explode because we have unlocked sort of a new level of capacity with our engine, right?
Right now, I think for software iteration is no longer a problem at all, right? But right now for the hardware iteration, it's still locked, even in China, right? So I think what we're building is having a much stronger implication is that we basically are unlocking the human innovation speed. I think that's the ultimate vision of our company. So that's always what I'm thinking is if something is out of our mind, whoop, then that thing, if ever that thing become just a general water or utility, right?
I almost
Yeah,
think of like how tokens have become so common now.
yeah, it's
Like
just like
it's
water.
like water,
Yeah,
right? So it's
yeah,
like you have
yeah,
ChatGPT,
yeah,
Claude now, so easy of making sort of an analysis of
yeah,
anything you need for daily tasks, right?
yeah,
Your tasks have been essentially tokenized
yeah.
with the number of tokens that are available. We're basically unlocking that for the precision industry.
Yeah.
Yes.
Like you're tokenizing the entire CNC industry and providing access to rapid prototyping at a scale that no one has seen before because our engine basically can process these components at scale.
Yeah.
And with AI, now you have sort of a level of infusion into the sort of design process of mechanical, if not more components. And we're starting first with the parts, right? But eventually it can go to assemblies, sub-assemblies, systems, and then full prototypes at scale. And AI is going to help design all this, right? So if we can unlock sort of the core physics of how to machine these parts, you're tokenizing that, making them more accessible with our AI stack, then the future of manufacturing kind of will sit on top of that building blocks. And I think that's going to be an amazing thing where now we're going to have an AI system that's really understands the geometry plus a system level of our stack and now can make new kind of geometries based on the material quantities we have, the material types we have. We have a lot of requests for doing crazy materials like titanium, magnesium alloys, there's carbon steel, there's all these kinds of new materials coming out right now in the sort of the new material space. We don't even know the full geometry of these things. And now with AI, we can unlock that and combine that with our kernel engine. You can start to make all kinds of new components in the future. I think that's exciting to me. I think, I know we've been in Texas visiting a bunch of locations. And I think, to me, I almost imagine like the U.S. sort of, as we continue to invest more in manufacturing, kind of thinking of centers of excellence that could become these sort of locations where people can make everything locally, right? And I think, what kind of drew me to Texas is, and obviously I think, we've been here for some time looking at ways to expand our footprint. And I think the recent launch of a lot of Tesla's new efforts in the semiconductor space with the Terafab, and also there's the Gigafactory here, and there's Samsung building their facility, and there's OpenAI building their facility in Abilene. Why do you think Texas is so different than like other places to build a factory? And I'm just curious, like, what do you guys think about that?
Well, I think there's the oil and gas groups in Houston. There's the tech corridor in Austin, and the kind of environs around Austin. I think the regulatory environment in Texas broadly makes it very attractive for companies. We've seen a lot of companies moving into Texas for a variety of reasons. I-35 also runs right up the middle of the country. Here in Austin, the airport's 20 minutes away from almost everywhere that has a manufacturing presence. So it makes a lot of sense to have this Texas Triangle be sort of what some people are kind of calling the new Shenzhen, because the Chinese are fantastic at manufacturing, but as we know, it's very difficult to just copy and paste a really efficient factory. You have to get the unit economics right. You have to get the logistics squared away, and you also have to have the demand to fill that factory capacity.
And I think stepping into that point of Shenzhen in Texas, like, I want to elaborate on that. What does that mean? Can you explain what that means or what that could mean, Bowen?
Yeah, so I think there's a very interesting quote on somewhere in Shenzhen. It's called "Time is money," right? So basically, is that for Shenzhen, the key is the iteration speed. I think based on some statistics, I think it can be up to 10 times in the past compared to China and US, right? So and then for Texas, it has all the foundations ready, right? But I think most important thing is the culture and people that made this happening, right? Uh, it is a people doing all the legislation, right? For the permitting, for the mindset of the local governor or local officials, right? They make things moving fast, moving easy, and get the strong support on SMB startups, everything, and also introduce the giants into this and be as attractive as possible. And another thing besides the culture and the people is obviously is location, because one is there's a lot of land still going on as we drove by I-35 everywhere, right? It's a massive opportunity, right? Two is it's close to the other country like the Mexico. It's close to where it can even loosen environment review or regulations, where we basically can build another bottleneck, which is a post processing, especially on the anodization, passivation. Those facilities can be built near the border between the Mexico and the Texas, and then we can build that on near in Monterey or in Torreon, in Saltillo, and then we can have a very fast ground transportations 2 to 3 times a day, and make sure that the parts can be fully vertically integrated, made in one or two provinces or one or two states across the maybe sometimes it's across borders.
Mhm.
Then it can be the central hub for supplying all the U.S.
Yeah, I think the opportunity in Texas is massive. I mean, there's plenty of land, there's lots of water, there's a lot of very intelligent, hardworking people
Yeah.
here who want to have these high skilled jobs and really put their shoulder against the wheel of this effort. And it's exciting. And there's a reason that Elon has come here. I mean, they let you build here. And so Texas is welcoming us with open arms. It's a great place to be. And yeah, I mean, to the point about logistics, I mean, I see us, and it's not silly to say it. You can have a facility cranking out all these parts, a bunch of self-driving Tesla, robo taxis or Cybertrucks, taking them on the road, QR code, and dropping them off at the client's doorstep, and coming back, charging, getting a new load, and heading back out again. Or drones taking things places, to your Amazon point. Yeah, it's very exciting to kind of see what is actually very, very nearly possible.
Yeah, and we'll also make the parts go into those as well.
That's right. Yeah.
And I'm always excited about sort of like how we can leverage the sort of the talent pool as well, because we talked a lot about skilled labor. I think Texas is an amazing place to build because you have hardworking people, as you mentioned, and there's a good software talent pool. I mean, I think of it as in a vertically integrated factory. You need to have strong software plus hardware people.
Mhm.
And I think, traditional factories, they typically have a certain sort of a mindset in place, but we're sort of changing that from like a waterfall approach to now an agile approach, like in software. And I think if we can truly figure out the right recipe, on how to make this factory, and then also build the recipe for our own components, I think it's going to be, essentially an order of magnitude of an effect on like the industry.
Yeah, I think from a man on the street perspective, there's a lot of doomerism about AI out there, but I think the element that is sort of under discussed is the abundance mindset and what this kind of technology can unlock and what AI will enable. And if you fast forward into the future, maybe a couple of decades, being able to manufacture something on demand democratically where you are is sort of the goal, and something that is doable and is in process. I think that redounds to the benefit of megacorps who there's a lot of waste in some of these processes that we are describing, how to alleviate pressure on designers, mechanical engineers, expanding margins, freeing up cash flow, bringing down the cost of the goods that are being shipped out into market. If you're a garage band startup, being able to prototype things quickly, readily and at a sort of a cost efficient basis is also quite helpful. It lowers the barrier of entry to really smart folks who want to get into a space but are otherwise prohibited by cost and time. So I see a lot of really, really cool benefits, being available to just everybody. And yeah, I
think democratizing advanced manufacturing is sort of like a big goal that I personally have. It's like I want anyone to make an insane part, right? And it's like right now AI has enabled people to do anything with software, but imagine that with hardware.
Yeah,
And
exactly.
that's exactly what I hit.
Yes.
It's like now you're decentralizing the whole process. You're not relying on a single source supplier. You have a network of facilities running on this AI stack that can essentially make components where you're at. And I think it's not even about the global tensions that we face. It's more about giving everyone independence to make what they want in their own geographical area, right?
Yeah.
And I think this is our vision. Is like we think of our company as a global identity of truly taking the technology stack and democratizing access to that and letting anyone use it. I could be in Europe or I could be in the US or any other high labor cost country and not worry about access to skilled labor or not worry about access to machines. I literally can just plug in, go to my website, log into APG, upload my design, and have a part shipped to me within a week or two, right? And that could happen locally or from a different neighboring country or from a place that you prefer. And that level of decentralization and democratizing that entire industry is, I think, huge.
Yeah, just want to add one point is the elephant in the room when people talking about one man company or one people company is what about the hardware, right? That in the future is that there will be true one man company that's also doable for hardware industries. That's where it is, because I don't think people can say right now we can do one man company for every industry. That's impossible. But with the help of us, I think there's a chance.
Well, yeah, there's that jokey meme out there that we were promised flying cars and we got 140 characters on a social media platform, but we're actually enabling the companies that are currently making the flying cars in the form of eVTOLs, and it's really exciting. And I'm hoping that we'll be able to hop in a eVTOL that has been made with parts that we've produced, and it's pretty exciting. So I'm actually very excited about the prospects of what AI is bringing us, and I think everybody else should be too.
I'm still thinking, always thinking of a magic wand situation, right? So if the customer will have a magic wand, what do they want right now, right? So what do they want right now? From what I see is they want to get what they quoted, what they see at the first place. They want a certainty, right? So for example, the oftentimes for our customer who needs a precision part assembly is they start all the process with a RFQ, right? Getting the quote. However, on the quote, there's always for any shop there will be an estimate on the cost and the lead time. But the most important thing is the lead time, especially on the R&D or the new product introduction, small batch phases, where it's the most important for every deep tech, hard tech company, right? So, but the magic wand they want is, can you keep the promise? Can you just see that as a covenant, right? So it's like a affidavit, right? So you get a stamp on, but always people have no hope on that, right? But the thing is, since our stack, the end-to-end AI stack, have the certainty at the beginning of the quote stages, because at the quote stages, we already know which machine it's gonna be machined on, what's the process is gonna be go through, right? And we show the entire simulation result to our customer just the first 5 minutes of the quote, right? So since everyone knows how to do this, right, in a consensus way, then we can keep the promise than the other shops, and this is the opportunity.
And I think it's important to identify how we're able to do this. So within our autonomous process generator software, APG, each datum, each annotation, each tolerance requirement, every single operation is not just identified, but also a cost is attached to that, so that during the DFM process, there is transparency, like ordering a pizza. You can know that it's being baked. You know where it's coming from, when it's about to arrive. And that is something that the industry has been really clamoring for, which speaks to what we mentioned a moment ago about that prisoner dilemma game theory
Yep.
and shops. Not to throw anybody under the bus necessarily, but just there's a lot of inconsistency, to put it generously, that attends and is a part of this industry because people are fighting to win orders. But then that hobbles the companies that are ordering the parts in the first place. It
Right.
slows down their development cycle, slows down their prototyping, their R&D, and ultimately their time to value, time to market. So we're able to step in and with software actually enable and empower these mechanical engineers, the entire organizations to move through their development process very quickly, know the costs associated with it, and actually get their products into the hands of people who are using them.
I 100% agree. I think, just in talking to some of our closest clients this week, we were in Austin, Texas, and looking at ways to expand our footprint here. And I think what I've noticed is that people really want to have a commitment to the process of lead time. And I think when we show them our software, I think there's a lot of excitement because most mechanical engineers, they spend a lot of time developing these 3D drawings and 2D drawings. And ultimately, they rely on the manufacturer like us to essentially execute on these drawings. And I think if we can start to enable them to have a DFM review at the very beginning of the design stage, then you can reduce that time of essentially making that part. And so, one of my favorite stories from one of our clients is talking about how, we're reducing the entire manufacturing design process because we're baking in the GD&T directly into our design tool. Right. Like, a lot of tools out there just give you an estimate on quote, but then we're going a step further, trying to essentially taking some of the annotations that as you mentioned on the 2D drawing and baking them inside of our 3D design. So we're creating our own custom, BREP form, which I think you should definitely share more about what BREP means. But that BREP format now stores all that key data sets, and now we can precisely create those process mapping for the CNC machines, and then create a process map, which then goes to our factory floor and then executes on that engine. And I think, if you look at the factory stack, right, a lot of companies out there are trying to do just quoting or just basic levels of just high level improvements to the stack. But we really think you have to do the whole vertical integration. I mean, that's just the quoting includes the process planning, includes the MES and manufacturing execution system, all the way down to the supply chain logistics, right? And I think how do you create that closed loop system to truly make a factory like replicable? And I think this idea of factories where we can sort of have a net mesh network of these facilities running on this centralized brain that's essentially deploying these instructions, I think is key. I almost think of the factory as like a computer where you have like the central chip that's processing the instructions and then passing that over to the rest of the nodes. And I think if you look at the machine shop, it kind of functions like that. You have the the inputs, which are the raw material, and you have the machine shop, the sector that cuts the material, and you have the quality station, which reviews, and then you also have this closed loop system that makes sure the whole factory is running according to the quality station metrics. And I think if we can start to digitize that whole factory and providing these sort of inspection reports as we iterate with these parts, I think that really starts to scale a system where you can actually franchise factories. Imagine like people can open up a factory within a month or two of just learning how the tools work, and now you have a network of these systems essentially running on our. Yeah, I just like how as we look at our stack, right? I mean, we're going again to the first principles of how you machine parts. And I think APG that we've created is sort of that sort of kernel engine that consists of the volume dissection and then the feature recognition and outputting the process parameters. And then you have the second layer, which is our factory OS, which essentially runs the shop floor like an AI, kitchen cook or shopkeeper, basically handling the orchestration of every machine, the robot, etc. I think if we get the initial layer done first robustly, then everything downstream is essentially executable based on that process planning engine, right? So the most important thing is ensuring that they call it the CAPP or the computer aided process planning
Yeah.
is as accurate as possible, so that you can go directly to the machine code.
Exactly.
Um,
And for the process planning, you have to be accurate. Also, you have to be flexible.
Yeah.
So that's where the interconnection with our first stack, the first layer and second layer, which is the APG and FactQuest, right? So what I mean by agile is like, so for example, it's quite often things that you're running out of one type of machines or you're running out of one type of toolings,
Mhm.
right? Then you basically, what that's indicate on the technology side is, while you're doing the process planning with the pipeline, AI pipeline that I described right now, you basically have for AI, there's a action space, right? So basically the art of this two layer stack is you can always muffle or mask certain action space, which is some machine are not choosable,
Mhm.
some tools are not available. Now, if you mask that, then the process planning gonna be regenerated within 5 to 10 minutes
Mm.
for a single part. Then it will be redirect towards the FastQuest, and it can run the show in the correct way, in the correct resources constraint.
Here we have a robot coupler that we are going to show how this part is produced through our APG system. Now, what you have to do is you upload the 3D design of this file, which is typically a STP or .stp file, and APG will decompose the volume of this file, apply feature recognition to detect the holes, the parameters, the chamfers, and then create a process toolpath for our factory OS system. And their factory OS system then plans the shop floor to execute on the instructions to machine this part at scale. And we take this APG plus FacOS and we deploy this in our vending system. Our unit factory then takes the vending system and autonomously makes this part at our factory. So let's share more about how this system works from the APG perspective.
All right. As you can see on the screen, here's our APG interface. You just go to code.acermfg.com and you can directly access to it. Then, as you can see here, you can just upload your step file, and you can up to 30 at one batch, but you can run even hundreds of them within several dozens of minutes. You can finish the entire results of batch results. All right, so after uploading, it would very quickly pre-processing to recognize all the metadata and to check if your file has corrupted or not. If it's corrupted, it will show the drawing has some issues. And if it's success, then it will show the status of created. Then after creating this part, what you can do is starting to configure this with a very easy several steps. First, you select the material for this part. Coupling parts, it's 6061 T6 aluminum alloys, and then there will be black anodizing requirement associated with it. And for R&D purposes, we probably just need 5 of them to begin with. And now you can select the global tolerances. Usually it's for this type tolerance parts, we select -F, the fine standards. What is most differentiating is we are building the AI native boundary representation, which is a BREP data format, which allows the user to attach any GD&T information onto this 3D files. Right, so GD&T is dimension intolerancing, as we all know, and we conform to the ASME Y14.9 standard. So as you can see here, we can create a datum around the center hole of it because it's a coupling, and as we getting this, we can create a perpendicularity GD&T onto the bottom surface of this. And as you can see, it's automatic showing the perpendicular relationship because we already registered this on our proprietary data structure. So we can have a 0.05, all right, and then this GD&T relationship is being established, and you can do more of this according to your critical tolerancing CTQ, which is critical to quality dimensioning and tolerancing. You can add those on, and later we'll introduce the feature to do 2D drawing automatic recognition on those critical to quality callouts, and will be automatically populating on the 3D data as we roll out the next version of this. Then once the user registers all the GD&T or non-standard, non-global tolerancing and dimensioning onto this, we can just generate a quote. And as you can see, after a minute or two, the entire analysis results, including the DFM results, which is by feature DFM, designed for manufacturability, will be coming out of this analysis results.
So as you can see here, we've uploaded the step file for this robot coupler, and APG is processing the entire DFM through their engine, and is computing a volume dissection and a feature recognition on that step file and computing the process results. So within a few minutes, you'll see a detailed mapping on how the milling process parameters work and how to machine this part to spec according to those GD&T tolerances and callouts that Bowen has showed us. Typically, this process can take much longer in traditional cycles where you have days review of DFM review with the supplier and manufacturer, if not weeks. And what we do here is we bake in a lot of that knowledge base inside of the software. So within minutes of uploading a design file, you have the immediate feedback. And this is key in order to make sure your designs are to spec and hit the right tolerances that you need from the manufacturer.
Yes, so this enables mechanical engineers to really speed up their lead time cycle, because usually there's this massive back and forth with a contract manufacturer where you're submitting your design, they're coming back with adjustments to it, modifications, edits, saying, our machinist can't do this or our machine can't do this, et cetera, et cetera. Whereas with APG, you're able to upload the step file and do all of those annotations, all of the callouts as a part of the GD&T annotation process. And it's AI defined there in the platform, in the system, automatically knowing which machines are going to be responsible for creating that part. So you shorten and compress that lead time, bring down the cost, et cetera.
Okay, the results came out in about 2 minutes, and let's see what it has for us, right? So the first thing first here is that we can just play the simulation of all the process planning it does on the real shop floor, which is So that's the full simulation of how we are about to machine this part entirely. So as you can see here, it's operation 1 and operation 2. And upon this is all the detailed breakdown of the feature by feature DFM results for its tooling, for why it cost this much, and also we associate any additional cost with the annotation results of the GD&T. Same thing for the milling tool. So basically, this tool is what we think it's a compiler, even a compiler in the early stage of the development. While we only have the 3D drawing, we want to check out how this part is costing or whether this design decision is wise or not. We can just use these tools in 2 minutes. 1 to 2 minutes, and we can check for a part if that design decision was wise or not. So that will increase the iteration speed by tens of folds. And another thing is we can see the impact of any post-processing requirement. For example, adding the black anodization will incur additional costs. And later on, we can also introduce if we do not do this post-processing. For example, we in R&D phase, we just want to test out certain amount of the function without matching with the ID industrial design requirement. We can try to not selecting this post-processing method and see how much lead time it will improve. That's what we call lead time-based DFM. And as you can see, all those parameters, timings, fixtures will be aggregated, and this is where we generated all the cost and pricing parameters with the tiered price, right? We can do 5 units all the way up to 500 units, and anything in between will show those tiered pricing immediately. So it's full transparency. You have the full control of your process, of your design decision, of your parameter, of your GD&T decision as well. So here it is. And if the customer click the submit quote button, and our vending system will just starting to orchestrate and starting to manufacture this part on the shop floor.
So this is live now. You can actually go to our website, log in, upload a part, and test it on our system. And as Bowen mentioned, as we compute the process parameters, our factory would automatically start making these parts to spec based on the requirements. And this APG software is the front end experience, but on the back end, our factory operating system is running to ensure that the part gets properly placed in queue on our shop floor. So many of our clients have various different kinds of tolerance requirements as they upload their part to our system. So our APG basically is quite flexible to accommodate these different GD&T callouts. And sometimes we're looking at the concentricity or like the perpendicularity or the datums need to be refined. And based on the kinds of part that we do, clients can upload their own sort of constraints to our system. A lot of times, what we notice with our clients is that they tend to over-constrain their designs. So they end up, adding too many tolerances, too many datums, and then that causes the system to be quite expensive to make. And what we do in our sense is by real time, we can show you that if you add this tolerance or this call out, you're going to have a certain cost increase or a cost change delta within your design. And this real-time feedback allows the design engineer to immediately change their system to reflect a design for manufacturability at the early stages. And I think this is key because you can be in robotics or in medical or in oil and gas, you can be in data centers, and these different kinds of parts require different kinds of tolerancing, GD&T requirements, and you can then design a spec. And APG supports all these designs uniquely because we store the custom BREP internally, and then we're able to adjust these parameters on the fly.
Yeah, it's important to call out the fact that every customer is different. And what we did when we built APG was bake in as much optionality as possible. So there are trade-offs. If you don't need every single fault tolerance to be incredibly high and you're really focused on lead time and just want to get that part in your hands as quickly as possible, you can relax those tolerances to boost the lead time and make it more efficient. Conversely, if it really is quite important, you don't care about lead time, you just need to make sure that the part is completely, precisely engineered to spec. That's also baked in, and that optionality is available to you.
The reason why we designed the interface to be white, or we call white box, as transparent as possible, is because we want to make sure that at the quoting phase, at the estimating phase, we already know what machine this part is going to do, what process it's already have, what's the deterministic tools it's already being generated and we have to order or we have stock. So all those things are being determined at the first 2 minutes of the parts is going through our APG system. So that's the entire total game changer we want to bring into this industry, is that we are not a marketplace. We are the factory as a product itself, so that we, because we have this vertically integrated strategy, that we can have this at the beginning of all the process. We already can predict what will happen. That's why we want to keep the best promises on those lead time, and we want to make sure the cost structure is as transparent as possible. That will bring additional benefits to while doing the R&D phase, is that because in R&D, time matters and also the certainty matters. We want to make sure like we offer this we offer this flexibility to remove certain kind of the post processing, such as anodization, or we can show how long our feature gonna cost you. It's gonna cost you time. It's gonna have a very long cycle time, and you can see that, and you probably can change the design around that to reduce that cycle time, in order to get these parts quicker without sacrificing the parts function at the designing phase. So that's why we make this transparent, and it's at the same time we showcase that what you see here is what you will get in the future at your front door of your company.
All right, so APG can also upload a batch of parts at the same time, simultaneously. So this is really useful for high mix components, which may have a robot that has an arm or a leg or a component. And you can see here that within minutes, you can upload a set of tens of parts, and the whole system will quote that thing simultaneously. And this is very advantageous because now you can, while you're waiting to do your next task, you can let the engine run, and you can check back in a couple of minutes or 10 minutes later. Now you have all the parts immediately quoted for you instantaneously. And now we're scaling this to not just tens of parts, but hundreds of parts. And so a typical bill of materials for a robot can consist of a lot of components. And so we want to make sure that the iteration speed is really fast for engineers designing this robot. And as you can see here, the system is auto-populating with all the components as we uploaded them, and it's auto-quoting them, doing the DFM review, doing the volume analysis, the feature recognition. And I can see here, you can assign the material property to this component, and it also tells you if you want to do some post-processing, and then also add the quantity. And then within that, it just adds that to the analysis feed and gives you an accurate quoting estimate for these sets of parts. A lot of times, MOQs, a lot of manufacturers ask you for MOQs. We actually don't ask for MOQs. We think our system is capable to do anywhere from one MOQ to thousands of parts, because our system on the back end can calculate, despite the number of parts you're helping to do, our engine can validate and estimate a quote for those parts. Now, obviously, if you have a higher MOQ order, the pricing would adjust corresponding to those higher MOQs.
Yeah, and it's important to add, I think, that really this is just empowering creators everywhere who historically have been kind of locked out of being able to pursue this kind of machining process because it historically has been cost prohibitive to create a prototype, submit a design, talk to a contract manufacturer for something that is really going to be an MOQ of one or two. With our platform, we're happy to enable this kind of creative design and bring this kind of process to anybody who wants to create anything.
So in summary, our AI native factories are really running on a core principle, which is optimizing the manufacturer design process for the industries like robotics, medical, oil and gas, and semiconductor industries. So we believe that in order to hit those key tolerances and lead times, you need to understand how these parts are machined to spec and done in a very, very fast lead time. Our tool is now live on aethermfg.com. You can actually go on there today, upload your parts, submit your quote, and we will provide you a very competitive lead time. Looking forward to sharing more as we iterate our stack, and looking forward to getting your feedback.